Hello and welcome to the second speedrun of today of the IB Math textbook with me, Vince. So, in this speedrun, we're going to be continuing our exploration of limits by looking at continuity. So yeah, let's jump right in. So, we were looking at limits before, and limits are especially useful for finding values of functions at when they don't actually exist at that point. But now we need to talk about continuity. So continuity is if a function is continuous, but that's a pretty bad definition. So the actual definition is it has to satisfy these three conditions. First, the function must be defined at a. So f of a must be defined. And so a is a part of the element of the domain of f. So that's one condition. The second condition is that the limit of f at a exists and is like a real number. So the limit of as x approaches a of f of x must exist, must be equal to some real number L. And finally, the third condition is that these two are equivalent. So if we get the function at a, it must be equal to the limit as x approaches a of f of x. So these are the three conditions it must satisfy to be a continuous function at this specific point a. So if it satisfies all three of these, then we can say f of x is continuous at x equals a. If it doesn't satisfy one of these three, then we can say it's discontinuous at that point. Okay, so now we need to talk a bit more about continuity. Now we've defined it. So if we give an interval, say if we give the points between 1 and 3, or actually just in more general terms, a and b, if a function is continuous for every point between a and b, then we say it is continuous for every point in this interval, which we will call I. And so a function is continuous everywhere if it is continuous throughout the real numbers. A function is continuous if it is continuous throughout its domain. So as long as the function is continuous for all values in its domain, it is continuous. And it's continuous everywhere if it's continuous for all real number values of x. And so a function that is not continuous is said to be discontinuous. So this raises a bunch of interesting things that you might not realize. Take the function 1 over x. You might think, oh, it's not continuous because it's not defined when x equals 0. But technically, this is a continuous function since its domain is such that x is not equal to 0. So it is actually a continuous function in its domain, but it is obviously not continuous everywhere. Okay, so now we've talked about that, we can move on to some questions, and again, I'll be doing the even ones. So first, we need to determine whether f of x is equal to x squared minus 1 when x is equal to 2, so it's a piecewise function, and 2x minus 1 when x is greater than 2 is continuous at x equals 2. So first, remember, we want to make sure that this value is defined in the function, and it is because it has a set value for it. The second thing is we need to ensure that the limit exists for this function. So as x approaches 2, it is defined. And the third thing is that the limit should be equal to the value of the function at that point. So now let's check for all three of those. So if we have, if we get the value of this function that at this point, which is 4 minus 1, 2 squared minus 1, that's equal to 3. So it does exist, that's fine. And the problem, therefore, is the limit of this function. okay, so we have 2x minus 1. And the problem being that, yes, we can solve that limit as x approaches 2 from the negative side of f of x, because this is simply 2. 2x minus 1 will approach 2. But the problem is we can't actually approach it from the positive side, since there are no values defined above 2. So actually this function is not continuous, this is discontinuous. Yeah. So, on to the next one. And the next function is we need to determine whether f of x is equal to x squared minus a squared over x minus a for all values where x is not equal to a, and 2a for all values for which x is equal to a. So we need to define whether this function is continuous at x equals a or not. So first, does a exist in the domain? Well, yes, it does. It's clearly defined and its value is 2a. Now, we can actually get the limit for this. So we have the limit as x approaches a. So let's first solve for the negative case of x squared minus a squared over x minus a. What would this function approach? As this approaches a, it's pretty hard to do this without a graph. But what we can, I guess, do is factorize this into x plus a times x minus a over x minus a. So, the thing is, if we're working in a limit, we can say that the limit of x, again, x tending to negative a is of x minus a over x minus a is equal to 1. Because even though it never approaches, like it never reaches this value, it will approach 1. And so this limit should therefore tend to x plus a, in this case is 2a. So since this value, actually this is true for not just the negative approach, but for the positive approach too. As these two values are equal, that means that this function is indeed continuous at this point. Okay, on to the next one. So we need to find the value of k such that f of x, so we need to find k, and such that f of x is equal to x squared minus 2, x is less than or equal to 2, and 3kx, when x is greater than negative 2, is continuous at x is equal to negative 2. So, more or less what we need to do here is we need to make it such that the limit as 3kx approaches negative 2 from the negative side is equal to, well, negative 2 squared minus 2, which is 2. This should be like, okay. Well, the limit as x approaches negative 2 of 3kx will simply be 3 times negative 2 times k. And if that's equal to 2, well, we need to make sure negative 6k is equal to 2, and so therefore k must be equal to negative 3. So yeah, that is it. Oh, sorry, not negative 3. What am I doing? Negative 1/3. My bad. Okay. And so finally, we have our final question. Well, actually 3 sub-questions. And for each of these, we need to determine whether each function is continuous on the set of real numbers. And if it's not continuous, state the values of x where this function is discontinuous. And so our first function is x squared plus 9 over x squared minus 9. And I would advise you to do this graphically before we go through some of the algebraic methods to determine. So we have, in this case, x squared plus 9 over x squared minus 9. And it should be pretty obvious that this is not continuous. As you can see, we have clear values for which there is like a jump between the values of y. So it's not continuous. What values would this be at? This would be at -3 and 3. Since for -3 and 3, this value here does not exist, and it flips between positive infinity to negative infinity, and from negative infinity to positive infinity. In this case, yeah, positive to negative and then negative to positive. Since the limit from the positive and the negative side are not equal, then this function is discontinuous at -3 and 3. And also because the function simply isn't defined for those numbers. So yeah. Now on to the next one. We have the function x over x squared plus 4. And this looks to be a pretty continuous function, but let's just check. X over x squared plus 4. As you can see, it's a continuous function. No real problems with this. Yeah. So as you can see, all points on this are continuous. There's not a single interruption in the graph or somewhere where it flips drastically, and so this is continuous. That's fine. And so the final function we want to look at is x squared over x squared minus 1. And immediately we should be able to tell this isn't continuous, since for the values of 1 and -1, this function is not defined at all. So we can check that by graphing it. So we have x squared over x squared minus 1. I think it's minus 1. Yeah. Oh, it's x cubed minus 1, but the result should still be the same. So x squared over x cubed minus 1, we can see that there is a clear, it's clearly not defined for when x equals 1. So that value, at that point, this function will not be continuous. So it will not be continuous for all real numbers. So yeah, that's pretty much it. I hope you enjoyed this video, and I hope to see you in the next one.